So in this clip, I want to just walk through some examples of momentum crossing the system boundary. And we're going to use a sort of simple kind of textbooky example for doing that. Imagine you've got a sled that's sliding along the ground. Nominally, let's call it a frictionless surface. And in one case, you have someone who runs and jumps on the sled from the back. In another case, the sled slides by and someone jumps on the sled from the side. And in the third case, the sled is going forward and someone jumps on the sled running in the opposite direction. And for each of these, I want us to think about a number of questions. The first question is just what happens to the mass of the system? And the way we're thinking about this is we're drawing a system boundary where the person actually is crossing the system boundary. So pretty clearly, if we think about mass, right, in all three cases, the mass increases as the person crosses that system boundary. So that's sort of the simplest question to ask is what happens to the mass of the system? Well, if you define it that way and you talk about the person crossing the system boundary, pretty clearly the mass increases. The second question that we can ask is about what happens to the momentum of the system in the x direction. And in order to talk about momentum, we have to decide what reference frame we're going to use. So we use the reference frame of just someone who's standing and watching this all on the ground. So this is a sort of stationary observer. And if you think about it from the stationary observer's perspective, what the stationary observer would say is that initially this sled has some momentum in the x direction. Maybe we'll talk about case 2 first. When this person jumps up and jumps back on, they cross the system boundary, but they cross the system boundary carrying no momentum in the x direction. And so both before and after the person has entered the system, the momentum in the x direction is the same. So p sub x is unchanged in case number 2. Okay. In case number 3, on the other hand, you can see that according to observer on the ground, the sled is going forward, it has some positive momentum in the x direction. A person comes along, the person is traveling to the left, they're carrying momentum in the negative x direction. So p sub x is going to decrease. It's going to become either 0 or negative, depending on how fast this person is running and how much the person's mass is compared to the sled's mass. And then finally, in case 1, as the person runs to catch up and jumps on, the person has a momentum in the x direction, the sled has a momentum in the x direction. When this person crosses the system boundary, they're carrying positive momentum in the x direction, so the momentum in the x direction increases. Okay. Finally, let's think about what the velocity is of the sled, right? And this is assuming that, of course, that once someone lands on the sled, they sort of stick to the sled. They've got good sticky tennis shoes on. Well, pretty clearly in this second case, it's easy to think about that from the stationary observer's perspective. The mass of the system is increased when the person crosses the boundary. The momentum of the system has not changed at all. And so the velocity of the system must actually have decreased in order to keep the momentum the same, right? Because the momentum is the mass of the system times the velocity of the system. If the mass goes up and the momentum doesn't change, the velocity must go down. By the same token here, if you initially had some positive velocity in the x direction, you do the same kind of argument. Mass is increasing, the momentum is actually decreasing. Pretty clearly in this case, the velocity of the system is going to decrease even more. And then finally, in this case, it's a little trickier to think about it. And the reason it's a little trickier to think about it is that we actually need to know not just that the person is traveling forward according to the stationary observer, we actually need to know how fast the person is traveling relative to the sled. Now, as we've talked about it, we've said the person has run to catch up and has jumped on. So we're assuming that this person is actually moving faster than the sled. That means that after this person jumps onto the sled, the velocity of the system actually is going to increase. And I encourage you to think about how it is that that would change if the person actually were jumping on going to the right, but were jumping on as the sled went by at a faster speed than their actual ability to jump. So sort of somewhere between case 1 and case 2, what's actually going to happen to the velocity in that case?